Good afternoon. My name is Luz Margarita Balcázar. I am a doctoral student at semester Zacatenco, Mexico City. My topic is effect of deposit condition on thin film synoxide indium deposited by ultrasonic chemical spray. The influence of indium concentrations on the optoelectric properties of synoxide indium thin films deposited by ultrasonic pyrolysis method was investigated, in which the deposition conditions such as substrate temperature range from 385 to 445 degrees Celsius, and the atomic ratio of impurity zinc in solution prepared with zinc acetate and indium acetate dissolved in a mixture of water, acetic acid, and methanol were varied by 1, 2, 3 weight% and deposited on glass substrate from an initial solution, being thus of synoxide indium doped at 3%, had the lowest resistivity, 2.2 times 10 to the minus 3 omega centimeters, a mobility of up to 12 square centimeters over volt second. At carrier concentrations in the range of 4.2-7.4 times 10 to the 20 centimeters to the minus 3 in an optical transmittance varying between 65 and 80% at 550 nanometers. For this work, we use ultrasonic spray pyrolysis, which is a useful method for obtaining synoxide thin films, due to its ease of operations and ability to coat large areas. Our objective is to perform a systematic study on the effect of two depositions variables such as substrate temperature and atomic percentage, and to analyze how they affect the physical properties on synoxide indium thin films obtained by ultrasonic chemical spray. The basic configuration of the ultrasonic chemical spray technique used in this poster is presented in Figure 1. Show the building schematic diagram of the experimental setup. It consists of a precursor solutions, an atomizer, substrate heater, temperature controller, gas carrier, ultrasonic generations, temperature control during the deposition process. We obtain the following result. In the Figure 2, show X-ray diffractions of undoped and indium-doped zinc oxide film on glass substrate and 450 Celsius degrees. X-ray diffractions allows obtain information of phases present, residual stresses, micro deformations, and crystallographic orientations. This structural characterization is used in order to corroborate the structure of the resulting synoxide films doped with indium, and to analyze to what extent the crystallinity of the films is affected when high concentrations of the impurifying agent are used. The result is all the diffraction peaks match very well to the Wurtzita sinusoid structure. The strong diffraction peaks indicate that the product exhibits good crystallinity. However, change in the intensity of the peaks were observed according to the position's conditions. It can be seen that the undoped sample show a preferential orientations in the plane 002, just like the samples deposited with the lowest dopant concentrations, but for samples deposited with higher doping concentrations, the preferential orientations change to the plane 101, which is obvious from the figures of texture coefficient. In Table 1 show the crystallity size, grain size, texture coefficient, and lattice constants of sinusoid indium. The Figure 3 show scanning electron micrograph. Undoped sinusoid thin film for 3 different radius, 1, 2, and 3% weight. All micrographs show the polycrystalline nature of the film with a surface covered by uniformly distributed grains. The particle size of films doped with 1% was larger than that of the undoped film. The 2% particle size was decreased and the microstructure of the film became denser. And 3% doped film consists of small homogeneous triangular particles. In electrical properties, the Figure 4 show variation of resistivity with temperature at different doping concentrations of indium acetate, variation of mobility and carrier concentration as a function of the substrate temperature for the 3% sinusoid indium thin film. The minimum resistivity value reached for films deposited from solutions with 3% radio was 2.2 times 10 to the minus 3 omega centimeters. The decrease in the resistivity with the increase in the indium concentrations can be attributed to the increase in the free carrier concentrations. In Table 2 shows the electrical and optical properties and sinusoid indium films at different dopant concentrations. Conclusions. Sinusoid indium thin films have been chemical spray on soda lime glass substrate. The effect of indium incorporation on structural, morphological, and optoelectrical properties of sinusoid film was investigated. All the deposited film were polycrystalline in nature. The indium incorporation affects the resistivity of sinusoid films. The lowest resistivity values of the order 1.6 times 10 to the minus 3 omega centimeters were obtained in films deposited with an ratio of 3% weight dopant concentration. The scanning electron micrograph showed that the surface morphology is affected by the indium content. Optimum substrate temperature for our system was found to be 430 degrees Celsius. The temperature plays an important role in determining optimum field growth and hence quality.